Welcome to Data Structure Learning at MITS CSE Data Science. In today's lecture, we are going to discuss the implementation of list ADT using linker list. Okay, this is the flow of presentation. How we are going to implement a linker list and what are the operations that can be done on list ADT using linker list and the different variations of linker list and its advantages and disadvantages and the comparison between array and linked list that we are going to discuss today. List ADT, the general definition that we are repeating from the previous lecture also. It's a collection of elements from A1, A2, A3, etc. up to AN. And the set of operations that can be done on a list is make empty, whether it is empty, we can check it is lost, find, delete, find previous, insert, delete list, advance and retrieve are the operations done on list ADT. And specifically here we discuss we have three different methods to implement the list: array, using linker list and using cursor. We have already seen how to implement the list ADT using arrays. Since the list is sequential arrangement of elements and we can perform insertion and deletion at any place, we implemented simply using array. In that array, we find a problem that we faced a difficulty where to perform insertion and deletion, at least we need half of the array to be moved either to the left or to the right to create space. So that make insertion and deletion into the list complicated. To overcome that problem, and also the second problem, we had to declare the size of array in earlier. To overcome these disadvantages from array, we are moving to implementing the list ADT using linker list. We will see what the linker list is. Linker list is collection of nodes that each node contains two fields basically. That will be, the first field is data field and the second field contains the address of next element to be found. Okay, so each node contains a data field and the address of next element. Okay, so only we can traverse sequentially. It retrieves an element and finds the address of next element. From this it goes to the next element. So it is used for holding data in an ordered sequential manner, and we can insert and remove any item at any place from the list with minimal cost. Okay, and we had a node that has a pointer locating the next node. Each node will be having the address of the next node to be retrieved. Generally, the last node will be having the null pointer at the place of next field. Okay, for the last nodes, it will not point to any other node, so it will be having the null pointer at that place. We will see the implementation of list using singly linker list. Singly, that means it forwards the collection of nodes in forward direction only. Each element contains the address and element and the address of next element. So it forwards. From first element we can retrieve second. From second we can retrieve the third element. From the third element it has the address of fourth element, we can retrieve it. So it moves in the forward direction. So it is singly linker list. Linker list is collection of nodes. Each node contains data field and the address field. Address field contains the address of next node. Right, so this is singly linker list. The last cell's next pointer, we are storing the null value as we specified here. This is node. In that node, the first part is element and the second part is pointer to the next element, that is next node. It holds the address of next node. Okay, then see how to declare a node. Since node contains element field and the next field contains the address of next node, we have to merge these two. We know structure will be using to store the variables with different data types. Here we have an element that may be of any type. It may be an integer list, or it may be a floating point list, or it may be a character list or string list, whatever may be the list of elements we may process. So according to the data type, we declare the first part, and then second part holds the address of next node. So we declare it as node type, struct node star. We are defining the node as structure, and the first byte element type may be any of the type, int, float, char, anything, and the element field. And the next field, it is struct node star next. That means self-referencing structures. This refers this holds the address of next node. Okay, and in the first lecture we have seen that why we have to dynamically allocate memory using this malloc and function, and we are deallocating that memory using free function. In a previous lecture itself we have discussed how to use this malloc function, right? So here we see the implementations of uh, list ADT using linked list. First thing, how to create a linked list. See here, I have created the linked list using 3 elements, and why we have given the first node as empty means this is the header node or dummy node. Okay, why we are maintaining this node means if we want to perform insertion and deletion at the first place, we need to perform insertion and deletion at the first place, it will change the beginning of list. Okay, for that we are maintaining a sentinel node called header node, so that we leave as blank, and from that next we are maintaining the list of elements, right? So see here, I have declared a struct node star L. So this is the beginning of address, that is the header node. From it we are creating if number of elements, it gets n as the input, number of elements to be stored at the beginning. So for each time it scans the element x and creates a temporary node. So in the name of temp, I am using malloc function to create a node. In that malloc, it uses size of function to find the size of node. That node contains element field and the address of next node. Okay, so the size of function calculates the node's size, and the malloc function allocates memory of that size and returns the address of that node that is stored in temp. So temp element means we are temp's element accessing the structure field with the help. Temp is the structure pointer, and we are accessing the structure element using the structure pointer temp. So temp arrow element. So this is temp. Temp's element is this place. Here we are storing this 26, right? And its next field will be and one more thing, I am making p here as a beginning, and since I am moving this from here to here, p equal to p next, and temp element equal to x, p next is equal to temp. This is p initially, so here we have copied p equal to l. So this is p initially, and I have given p next equal to temp. So this is p next. This position instead of null, I am pointing to this address. So this link will be created, and then temps next is this place that I am storing null at the initial position, and p equal to p next. Now I am moving p from here to here, and the loop continues. So each time this is p, it creates a new node in the name of temp and stores the value of x here, and p is next equal to temp. This link will be created and this will be made as null. and in the next iteration it creates new node. It frames this link, stores the element and makes it null. So if the loop iterates until we give how many number of elements we are going to create. So like this the loop iterates, and each time a node is created in the name of temp and it is attached to the end of list L, right? So by this we are creating the linked list, and we have created the linked list as we have shown in the up. And the number of operations that can be performed are insertion, the main operations: insertion, deletion, find and find previous. Okay, and since it is list, we can insert at any place. We will see one by one. If we want to insert at the middle, we are performing just the element x to be inserted, and p is the position where we need to insert, and L is the list on which we have to perform insertion. So just if you want to insert, I have to allocate first node. So for in the name of temp, I am calling malloc function to declare to allocate a node. So node is created in the name of temp, and for the temp element I am storing the value of x as here. Now I have to just readjust this pointer between p and p next node. This is p node. At this position we have to insert, and so we have to readjust this link. Instead of this link, I have to make this to point here and this to point here. So for this, first we are the address of this node, the 35's address will be at p next, right? At p next, 35's address will be at the position p next that I am copying to here. So temp next is equal to p next, and p next is equal, so the right side link will be established. And then if I write p next is equal to temp, this place will be copied with the address of temp, so the left side link will be established. This link gets cut, and this link is formed, readjusted. So now if we check the list, it will traverse as 26, 56, 35 and 12. We have performed insertion at in between. Any place we can perform, at any position we can do like this, right? And insert at the beginning. To perform insertion at the beginning, no need to find no need of any position that to be inserted. We just be passing the input parameters. X is the element to be inserted, and L is the list on which we perform insertion, right? So just I am using malloc function to I have declared the temp as a node, and for temp node I am calling malloc function. A new node will be created. I am storing this value temp element equal to x, so it will be stored, and then temp next is equal to L next. Okay, so what is L next? L, the first element's address, that is stored in the place of temp next. So right side connection established, and then L next is equal to temp. So instead of pointing to 26, it will point to 56. So the header node points to 56, and then 56 to 26. Likewise, it goes on traversing. Okay, so this is insertion at the beginning. Next, to perform insertion at the last. To perform insertion at the last, what we need to do? For we know only the address of header node. At any time, we will be having the address of first node only. So, to perform insertion at the last, we have to traverse the list from here to the end. How we find end? By this null. If this is the last node's next field will be having null. Based on that condition, we are traversing the list from L, that is from the header node to the last node. See here, I am taking backup of L in the name of P, and I am traversing that P until P next not equal to null. We perform P equal to P next. So P is initially this is the P node. So P next this field, it is not equal to null. So we are making P equal to P next. So it will move here. So again its next field not equal to null, P equal to P next, it moves here. Again it checks not equal to null, it moves here. So yes, its next field is equal to null, it stops. The loop stops with here. This is the position P. Right. So this is the position P. So from here we have to attach the new node. So we create new node in the name of temp, and we are storing temp element equal to x. So 56 is stored here, and just instead of already we have p next is equal to null, instead of that we are storing p next is equal to temp. So the address of temp node will be assigned at this position, right? And then we are making this temp next field as null. Like this the element is inserted at the last position, right? Similarly, we can perform delete operations at different places. Um, we perform deletion at the middle position, right? To perform deletion at the mid position, first we have to find where the element is. Okay, so if I retrieve this element, I can't go before this. Only we can forward in the right direction. We can't go backwards in this linked list, since the node is having only the address of next element. It is not having address of previous element. So what we are doing to perform deletion, we are making use of find previous. Okay, so I call a function C here, P equal to find previous of x comma L. So it returns the address of previous node of L of x. X is the element to be deleted. So it returns the previous node's address. X previous node's address will be returned as P. See here 35 is the node to be deleted in our example. So if I call find previous we will see later how to perform how to find previous. So 20 address of 26 will be returned as P, right? As per here P equal to find previous, it will be returned. Now the next node, P's next node is the node to be deleted. I am storing that node as in the name of temp equal to P next. This is P, so this will be P next. So that is saved in the name of temp, right? And then P next is equal to temp next. See here, I have to bypass these two links, and I have to, the next field of P should point to the node next to temp, right? So it has to bypass this node. So for this is temp, this node's address will be in temp next. So we are storing P next is equal to temp next. It will be, this link will be created, and we are freeing the temp cell. This node will be, if we call free function, that node will be deallocated in the memory. Like this we perform deletion at the mid position, right? And to perform deletion at the beginning, the same scenario, there we used find previous to retrieve the element. Here no need of element x, since whatever element is at the first position we are going to delete it. Okay, no need of searching an element, just whatever element is at the first position we are going to delete. So the first node is header node. The header node points to 26, that I have to change as it pointing to 35. That's the thing we want to do. So L next is 26, that we are copying the name of temp. I give the name temp as for this node. Okay, and then instead of L pointing to this node, we are making L pointing to the node next to temp. So L next is equal to temp next, because this node's address will be here only, no. So this is temp next. So that value we are copying to L, right? L next. So L next is temp equal to temp next, and then we are freeing the temp cell. Okay, so like this we have deleted the first element. And to delete an element at the last, just we have to traverse the list as we do for insertion at the last. here we have to traverse from the beginning to the last, but one thing, we have to stop one step before. Okay, because if we stop here, we can't delete the same node, so we have to stop at this position. So how to write the condition? If that any particular nodes next field is null, we have to stop here itself. That is the criteria. We are starting from here, and from this place I am checking this place. From this node itself I am checking the next position of next node, right? So if this is null, I will stop from here itself. So why p equal to L means this is p initially, and p next. If this is p, this is p next, and p next will be this field. If this is not equal to null, we are making p equal to p next. So it is not equal to null, it will move here. So from here we are checking this position. Yes, it is not equal to null, we move here. From here we are checking this position, it's equal to null, the loop gets stopped. Once it exits out of the loop, this is p, right? 35 is p. The next node to p is the node to be deleted, that I am assigning the name of temp equal to p next. Okay, so this is the node to be deleted, temp, and then I am making the next field of p to be null. I am cutting this link, so p next is equal to null, and later on I am freeing this temp cell. This is the way how we perform deletion at the last position. Okay, and the main operation, how to perform find. We are searching for the element, so we have to traverse the linked list from the header node to the last node, and we are checking whether it is equal to that element. If it is equal, just we are returning the position at where the element is find. So see here, x I have given as 12, that is the element to be searched here in the list L. Okay, L represents the beginning of linked list. So from here, since if I use L to traverse, we will lose the beginning of linked list later on. Okay, if I use the same L to traverse the list L equal to L next, if we write like this, what's the problem means, for using another functions, we will lose the beginning of linked list. We don't have any backup, no. So always we start copying backup, and then we are going to traverse that node alone. Okay, so I have declared a temporary node called p. In that node I am taking L next. So if it is L next will be this node. So if it is not equal to null, and then its element is not equal to x, until its element is not equal to x, it will be keep on traversing. So yes, this is not equal to null, so it will be having some value. So it checks for the value not equal, so it moves to next position. Again it has some address, its if an element is not equal to x, it keeps on moving. Again p not equal to null, and p's element equal to x, it exits out of the loop and returns p as the position where the element is found, right? So like this we are finding the difference between find and find previous is that uh, for finding an element, it retrieves the node first and then checks for the value at the node. Okay, since we need the position where it is found, so we are first accessing the node. Always if we are checking 26, this will be p. If we are checking with 35, this will be p. So first thing we are accessing that particular node, and then we are checking for that value. But in find previous, we will be checking the next node's value from previous nodes itself, because we have to stop one step before, no. So for find previous, the difference between find and find previous I am telling. Here we will be starting with we have started with p equal to L, right? P equal to L next we have started in find, but in find previous we will be starting with p equal to L. So from the first node we are starting, and From this node, I am checking the value of 26 whether it is equal to x, right? So from P is here, from here P says P next not equal to null. So there is next something next node. So on next node's value not equal to x, yes it is not equal to x, it keeps on moving. And place of 12 we will be uh, if P is at here, yes P is next not equal to null, so there is some next node, and next node's value is equal to 12, it exits out of this while loop and returns P. So address of 35 will be returned, that is the previous of 12. So previous position is returned. Where we are using this find previous function means it is useful in performing deletion operation at in between, okay, at in between places. So for performing deletion at the middle we need find previous function, so we are implementing this find previous. The difference between find and find previous is, for performing find operation first we will be accessing that node, and from that node we are checking whether that node's value is equal to x or not. But in find previous we are in the previous node, and from previous node we are accessing the value of next node, and we are checking whether it is equal to the x, right? From previous node we are checking the value of next node. If it is equal, we stop with that and we return the position, okay, previous position is returned. And then how to display the linked list, just we are beginning starting from the structure L, okay, so that is linked list beginning will be in the L represents the address of header node, and from here it access each node by traversing through P equal to P next. So from P I am copying L next, so the first node's address, and I am until it is not equal to null, each time I print the element and perform the traversal P equal to P next. With this statement P equal to P next, I can traverse to the end. I can traverse the list till the end. So first time this is P and I am printing this element, and P equal to P next, this will be P. I am printing this element, and P equal to P next, this is P. I am printing this element. And in the fourth time, if I give as P equal to P next, that P will be reaching null. So it is equal to null, the while loop gets exited, right? While loop gets exited. By this we are displaying the linked list, okay. And these are the various, we have some variations in the linked list. The problem that we identified with the singly linked list is we can traverse only in the forward direction, that is it can access only the next element, we can't go backwards, we can't retrieve the previous element. So these are some we face some, and the address of last element pointing to next field of last element pointing to the null. Each time we have to begin from the header node and we have to keep on traversing. To overcome this we have number of variations. See this first variation, circular linked list. In circular linked list, what's the difference between singly linked list and circular linked list is, instead of the last node's next field pointing to null, the last node's next field will be having the address of first node. It will be pointing to header node. Okay. So wherever we can, if we are at the last, we can just access the first element. No need to again start from the beginning. Okay. So this is circular linked list. And the second type, doubly linked list. To access the address of previous element, we are using doubly linked list. So here each node will be having an element and two pointers. Okay, pointer to the previous element and a pointer to the next element. One pointer holds the address of next element, and one field holds the address of previous element. So first node's previous element is null, and last node's previous element will be, now last node's next element will be pointing null. Okay, header node's previous field will be pointing null. Okay, this is header node's previous field will be pointing null, and last node's next field will be pointing null. Okay, then each node has three partitions. So for declaring the node of this type, we have to use three fields: two pointer, that is struct node star previous and struct node star next, and one data field element type element. Okay, and doubly circular linked list, the same as circular linked list. First node's previous field will be pointing the address of last node, and last node's next pointer will be pointing the address of header node. Right? First node's previous pointer will be pointing the address of last node. Then last node's next pointer will be pointing the address of uh, first node. Okay, so this is doubly circular linked list. These are the variations of linked list we have. Then we'll discuss the advantages of using linked list. As in array, we have to declare a static memory. We need to know the size of array in advance. But since in linked list we are dynamically allocating each node, it is memory efficient, and whenever we need, we are declaring that using malloc function. We are declaring a node and we are using. And for insertion and deletion, just we are making pointer adjustments, so it is very easier compared with the array. And with constant time we can access these the elements in the list. And the disadvantages of using linked list is we have to maintain pointers that make it complicated. Okay, uh, and only we can traverse from the begin from the first to last, that is we can access sequentially the elements. We cannot pick an element random at a fifth position, at seventh position we cannot pick an element at random, only we can traverse sequentially. Okay, and we are using extra memory to store the address of next node. For that we need some extra memory. And when compared with arrays, searching can be done in linear time in arrays, but here it takes time when compared with arrays. So we'll see the difference between array and linked list. We have already discussed that insert and delete operation is complicated in array. Here in linked list we can perform it easily. And element of array stored in continuous memory allocation. In linked list, each time we are calling malloc function to create a node, that is not necessary to be in adjacent locations. Wherever the free space, it will allocate memory. Okay, we are retrieving the next element by using that next pointer alone. Okay, and for inserting and deleting at the array, we have to create space for it. We have to move the element left or right. But in linked list, we are just rearranging the pointers, and we are readjusting the pointer links alone. We are not moving the copying elements in the node. We are not copying the elements in the node. Just we are making one new temporary node, and we are making pointer adjustments alone. So sorting be efficient in array, but difficult in linked list. Okay, since we have to traverse through the next field each time to retrieve the next element, the sorting becomes difficult in using linked list. The linked list array uses static memory, and linked list uses dynamic memory. Since static memory is allocation is used in array, it uses more memory, and many more memory gets wasted there. And since the linked list utilizes dynamic memory allocation, the memory is utilized efficiently. Here we have discussed the implementation of list ADT using singly linked list, and what are the variations in singly linked list. Variations of linked list we have seen. that is a singular linked list, circular linked list, doubly linked list, circular doubly linked list we have seen. And what are the difference between all these things we have discussed. And the advantages and disadvantages of using linked list we have seen. Advantage is that insertion and deletion becomes easier. Disadvantage, we have to allocate and we can read only sequentially. That is disadvantage of linked list. And then we have seen the comparison between array and linked list. And in the next lecture we will discuss the applications and the real-time scenarios where we are using this list ADT in detail. And if you have any queries, any clarifications needed, you just leave your queries in the form given, and that will be discussed in the upcoming lectures. Right. Thank you.